Welcome to rotational motion. Previously, when we were studying circular motion, we looked at these equations. We have displacement and angular displacement. We have velocity, also known as angular speed, and we have angular velocity. Notice the terms angular velocity, angular speed. This has the same magnitude, but is a scalar. We have acceleration and angular acceleration. And finally, centripetal acceleration and centripetal force. Angular velocity is the rate of change of angular displacement, and angular acceleration is the rate of change of angular velocity. Rotational motion can be thought of as linear motion around a fixed point, and there are many analogies linking the two together. For example, in linear motion we have mass, and in circular motion we have the moment of inertia. In linear motion we have force, and in circular motion we have torque. We can also draw parallels with the Suvat equations, or the equations of motion. For displacement, we have angular displacement. For the initial velocity, we have angular velocity 1. For the final velocity, we have angular velocity 2. For acceleration, we have angular acceleration, and time is the same. If we take the equations of motion, then we can rewrite these just using the circular motion terms. And these equations are completely correct. You can use these to solve Suvat-like questions in a circular motion context. Another similarity are the motion graphs. Here we have displacement time, velocity time, and acceleration time axes. And on the right, we have angular displacement time, angular velocity time, and angular acceleration time axes. I will draw the same curve for both of the graphs at the top, and then we will analyze them. So we have a low gradient reaching a peak, and then reducing to 0. And again, a low gradient reaching a peak, and then reducing to 0. I'll mark the point where the gradient is at its highest, and the point where the gradient reaches 0. And I'll do the same for rotational motion. We know that velocity is the rate of change of displacement, and we know that angular velocity is the rate of change of angular displacement. So these graphs will show the gradient of the one above. Gradient is increasing to a maximum and then reducing slowly to 0. Here, gradient is increasing to a maximum and decreasing to 0. We know that acceleration is the rate of change of velocity, and we know that angular acceleration is the rate of change of angular velocity. So again, the next two graphs will show the gradient of the one above. So we have a positive constant gradient, which then becomes negative. We have a high positive gradient, which then becomes a negative value. So as you can see, for circular motion, the motion graphs behave in the same way as they do for linear motion.